Above the northern horizon, where the dark sky turns slowly around an unseen point, one star appears to hold still, night after night, century after century. Polaris waits in almost the same place, a pale marker above the turning Earth. Ships have crossed black water beneath it. Travelers have followed it through cold air and open land. Yet the closer science looks at this familiar light, the less simple it becomes. Polaris is not only a guide. It is a system of stars, bound together in slow orbits, wrapped in questions about distance, age, brightness, and time. The point of light that seems so steady from the ground is pulsing, shifting, and refusing to fit neatly into the models built to explain it. Around that mystery, a wider story begins to open. Some stars breathe in regular waves of light and become markers for measuring galaxies. Some swell until their outer layers would reach beyond the orbits of planets. Some hide behind dust of their own making. Some burn so violently that their short lives scatter the ingredients of future worlds into the dark. Before the path moves deeper into that quiet, stellar landscape, take a moment to settle in. If this kind of calm space documentary belongs in the night with you, consider subscribing, leaving a like, or sharing it with someone who listens to the universe while resting, right where you are watching from. And what hour it is where the sky outside your room has gone dark. Let the light soften. Let the screen become less important than the voice. Somewhere beyond the window, the stars are still moving, even the one that seems not to move at all. And from that still point, the story can begin. On a clear northern night, after the last warmth has faded from the ground, the sky begins its slow turning. It does not move quickly enough for the eye to catch. Nothing rushes. Nothing breaks the silence. Yet over the course of the night, the stars that first appeared above the eastern horizon climb higher, lean westward, and slowly change their places against the dark. The constellations seem fixed only for a moment. Given enough time, they reveal the motion hidden inside the night. The Big Dipper tilts around the pole. Cassiopeia rises on one side of the northern sky and later sinks on the other. In winter, Orion lifts his bright belt over the southern horizon. In summer, the pale river of the Milky Way stretches overhead. Every part of the sky appears to take part in the same quiet rotation. Near the center of that turning, one star hardly moves. Polaris is not the brightest star in the sky. It does not have the sharp blue-white light of Sirius, or the orange fire of Arcturus, or the red glow of Betelgeuse in Orion's shoulder. To the unaided eye, it looks modest. A small point, a steady point, easy to miss unless the eye knows where to search. And yet, for much of human history, this quiet star mattered more than almost any other. Sailors watched for it above dark water. Travelers looked for it over open land. Astronomers used it as a marker in the northern sky. A person standing beneath a clear night could find the Big Dipper, follow the two outer stars of its bowl, and let that imaginary line climb upward until it reached a pale star standing near the north celestial pole. That star was Polaris. Not a blazing object, not a dramatic one, a marker. Its power came from position. The Earth turns once each day around an invisible axis running through its north and south poles. If that axis could be extended outward into space, beyond the air, beyond the moon, beyond the quiet paths of the planets, it would point very close to Polaris. The match is not perfect. Polaris sits slightly away from the exact pole, and through a long exposure photograph it draws a tiny circle in the sky. But compared with the broad arcs traced by the other stars, that circle is so small that human eyes read it as stillness. The rest of the northern sky appears to move around it. This simple geometry gave Polaris its old importance. In the northern hemisphere, its height above the horizon roughly matches the observer's latitude. Near the equator, it rests low, close to the edge of the world. Farther north, it climbs higher. At the North Pole, it would appear almost directly overhead, while the other stars circle around it without rising and setting in the usual way. South of the equator, Polaris disappears completely. The Earth itself blocks the view. Before satellites, before radio navigation, before a map could glow from a small screen. This was not merely an interesting fact. It was a way to survive. A star that kept its place could become a direction. A direction could become a route. A route could become a way home. Polaris did not need to be understood as a yellow supergiant. It did not need to be known as a variable star or as part of a system with hidden companions. For the old navigators, it only needed to remain where the northern night expected it to be. For centuries, that was enough. From the ground, Polaris seems simple. One star, one point of light, a quiet anchor for a rotating sky. It invites trust because it appears to change so little. The moon changes shape. Planets wander from one constellation to another. Meteors appear and vanish in a breath. Clouds erase the heavens for hours, then clear again. But when the northern sky returns, Polaris is almost where memory left it. That steadiness is real, but only in the human sense. On deeper timescales, even the North Star is temporary. Earth does not spin like a perfect machine aimed forever in one direction. Its axis wobbles slowly, like the axis of a spinning top, tracing a broad circle across the sky over thousands of years. This motion is called axial precession. It is far too slow to notice in a single life, yet it changes the stars that stand near the pole. Long before Polaris held its place, the bright star Vega lay closer to that northern point. Far in the future, Vega will come near it again. Polaris is the North Star now, but not always. Its stillness belongs to an age. It belongs to the present arrangement of Earth, sky, and human history. That makes the star feel even more delicate. The stillness is not a permanent command. It is a coincidence that lasts long enough to shape civilizations. The star itself is not motionless. It moves through the Milky Way like every other star, carried by the long rotation of the galaxy and by its own path through space. It only appears fixed because it is distant and because Earth happens to turn beneath it in just the right way. The illusion does not make Polaris less useful. It makes it stranger. A star can be a guide because of an accident of geometry. A point of light can feel eternal because human lives are brief. There is a quiet beauty in that. The light from Polaris has crossed hundreds of years of space before reaching Earth. It began at the surface of a star far larger and brighter than the Sun, then moved outward through the darkness at the fastest speed nature allows. It traveled through regions of interstellar dust too thin to be touched, through the wide silence between neighboring stars, and finally into the atmosphere of a small planet turning in the dark. Some of that light scattered in the air. Some of it reached the ground. Some of it entered an eye looking north. In that moment, something enormous became small. A star many times wider than the Sun became a point. A point became a direction. A direction became a human feeling of orientation beneath the night sky. This is why Polaris has remained in memory for so long. It does not merely shine. It makes the sky seem readable, but the more carefully it is studied, the less simple it becomes. The star that appears alone is not alone. The light that seems steady is not perfectly steady. The distance to it, which should feel easy to measure for such a famous star, has resisted certainty. Its rhythm, mass, age, and companions all carry small disagreements that do not vanish when better instruments are turned toward it. In a strange way, modern astronomy begins by disturbing the old trust in Polaris, not to destroy it, but to deepen it. To the ancient navigator, Polaris answered a simple question: where is north? To modern astronomy, it asks quieter and harder questions. How far away is it, exactly? How old is it? Why does it pulse as it does? Why do its measurements not fit as neatly as they should? Why does one of the most familiar stars in the sky remain so difficult to place inside a model? The honest answer is that Polaris is still being understood. This makes it a fitting doorway into the lives of stars. From the surface of the night sky, it seems calm. Beneath that calm, there are slow orbits, hidden companions, stellar pulses, and measurements so fine that even a tiny uncertainty can change the story. The North Star becomes more than a guide for travelers. It becomes a guide into the limits of measurement itself. For now, it remains above the northern horizon. The sky turns around it. The constellations drift through their silent arcs. The old wheel of night continues to move, and near its center, a pale light holds its place. Not forever, but long enough. From the ground, Polaris appears solitary. A pale point above the northern horizon. A single light holding near the center of the turning sky. Nothing about its quiet appearance suggests a system of stars, or a set of hidden motions, or a gravitational arrangement unfolding across distances too wide for the eye to separate. This is one of the first lessons the night teaches slowly. Many stars that look alone are not alone at all. The human eye is good at finding patterns, but it is not built to divide small angles in deep space. Two stars can stand far apart in reality and still blur into one point from Earth. One star can hide beside another if the brighter one overwhelms the fainter light. The sky often simplifies what is there. It turns systems into dots. It turns motion into stillness. It turns companions into silence. For a long time, Polaris was one of those simplified lights. Through ordinary sight, it gave no sign of company. It seemed to shine by itself, fixed near the pole, clean and dependable. But when telescopes began to gather more light than the eye could hold, that simplicity began to loosen. In the late 18th century, William Herschel turned a telescope toward the North Star and saw that Polaris had a visible companion. The point of light was not perfectly singular. Near it, separated widely enough for careful observation, another star was present. That companion is now known as Polaris B. It is much fainter than the primary star, and from Earth it lies in the glare of a much brighter neighbor. Yet it is real, bound to the system by gravity, moving slowly around the inner pair in an orbit so large that a human lifetime catches almost none of it. If the primary star is the lamp by which the system is known, Polaris B is the distant attendant, quiet and pale, circling on a path measured not in years as people experience them, but in tens of thousands of years. A wide companion, however, was only the first hidden layer. More than a century after Herschel's observation, another clue appeared, not through a direct image, but through motion written into starlight. When a star moves toward Earth, the lines in its spectrum shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. This is called radial velocity, a movement along the line of sight, and it can reveal what the telescope cannot separate. Polaris A, the bright star at the center of the familiar point, was not moving as a single isolated star should. Its light carried a rhythm of approach and retreat, small but measurable, as though something unseen were tugging it back and forth. That unseen object became Polaris AB. The companion was too close to the main star to be easily seen. It lived inside the glare, hidden beside the much brighter primary, like a small lamp placed next to a lantern. But gravity left its signature. The visible star wobbled, its spectrum shifted. The light itself became evidence of a body that the eye could not resolve. Only much later did direct imaging confirm what motion had already suggested. With instruments sharp enough to separate fine detail close to a bright star, astronomers finally saw the close companion. The North Star, which had seemed so simple from the ground, was a triple system: Polaris AA, Polaris AB, and Polaris B. The names are plain, but the arrangement is not. Polaris AA is the star that dominates the system. It is the one that supplies almost all the visible light. It is the star people mean when they speak of Polaris as the North Star, larger, brighter, and more evolved than the Sun. It has moved beyond the calm, middle portion of stellar life. Its outer layers have expanded. Its light is warm compared with the hard blue light of the hottest stars. Yet it is far more luminous than the Sun because its surface is spread across a much larger sphere. Close to it, Polaris AB follows a long, slow orbit. The two form the inner pair, a binary system wrapped tightly compared with the great outer orbit of Polaris B. They do not simply sit beside each other in space. They circle a shared center of mass, an invisible balancing point between them. Polaris AA is heavier and brighter, so that center lies closer to it, but it is still pulled. Its path is not straight. It sways under the influence of its companion. The motion is patient, but not still. Farther out, Polaris B circles the inner pair from a much greater distance. Its orbit is so wide that the entire recorded history of telescopic astronomy shows only a fraction of its journey. It is not a close dance like the inner binary. It is more like a distant circuit around a central fire, a slow bond held across a dark gulf. This layered structure is common in the galaxy. Many stars are born with companions. Some form in pairs, some in triples, some in richer groups that later scatter as their birth clouds dissolve. A lone star, like the Sun, is not the only normal outcome of star formation. In cold clouds of gas and dust, gravity does not always collapse matter into a single center. The cloud can fragment. Separate knots can condense. Several young stars can emerge from the same nursery and remain bound, their future paths shaped by the mass they inherit and the orbits they settle into. Polaris carries that history inside its present light. Its companions matter because they change how the system is understood. A star's brightness alone does not tell the whole story if some of the light is shared with another body. A star's motion cannot be interpreted as isolated if gravity is pulling from nearby. A star's age becomes harder to place if its companions seem to tell a different story. The more carefully Polaris is measured, the more the companions have to be included. The first companion, Polaris B, is much dimmer than the primary, but it is not insignificant. It is a yellow-white star with a mass somewhat greater than the Sunday star. In another part of the sky, far from the glare of Polaris AA, it would be a star worthy of its own quiet attention. Here, it is easily overshadowed. The main star floods the system with brightness, and the smaller companions become difficult to study with the same certainty. The close companion is more difficult still. Polaris AB sits close enough to the primary that separating the two is like trying to see a small candle beside a bright street lamp from a great distance. The problem is not only faintness, it is contrast. The brighter source spreads its light through the instrument, and the fainter one must be extracted from that brightness with care. In astronomy, seeing something often means learning how to remove what is too bright. That difficulty gives Polaris a strange double nature. It is easy to find and hard to measure. It is famous, but not simple. It is visible to the unaided eye, yet the full system had to be unfolded across centuries of observation. A telescope revealed one companion. Spectroscopy revealed another. Later imaging confirmed the close star. Each method opened a different door. Direct sight found what was far enough from the glare. Motion found what light could not separate. High-resolution instruments finally showed what earlier tools could only infer. Polaris became not just an object, but a record of how astronomy itself learns to see. There is a softness to the system when imagined from far away. 3 stars bound in darkness, turning through time at different scales. One bright and swollen, one close and hidden, one distant and faint. The inner pair moves through its orbit, while the outer companion traces a much larger path around them. All of them travel together through the Milky Way, carried by the galaxy's slow rotation, while Earth turns beneath their light. From the surface of this planet, none of that motion is obvious. The old appearance remains. Polaris still looks like a single star. The northern sky still turns around it. Its usefulness has not changed because its structure is more complicated than it once seemed. A compass needle does not need to know the geology beneath a mountain. A traveler does not need to know the hidden companions of a star to use it for direction. But astronomy asks for more than usefulness. It asks what the light is made of, where the motion comes from, how the system formed, and why its pieces do not always fit comfortably together. In the case of Polaris, the companions are not decorative details. They are part of the problem. They may affect how the primary star moves. They may complicate the measurement of its distance and brightness. They may hold clues to its age. They may even help explain why this familiar North Star behaves less like a simple standard and more like a system still refusing to settle into one clean answer. The eye sees one star, the instruments find 3, and between those 2 views, the old North Star begins to change. It remains the same point in the sky, but it is no longer the same idea. It is no longer only a marker above the horizon. It is a small, stellar family, bound by gravity, wrapped in glare, and slowly revealing itself through the patient work of observation. In the quiet northern night, the difference is invisible. Polaris still holds its place near the pole. The stars still wheel around it. The dark still seems to turn on that pale point. But inside that point, there is motion. The brightest member of the Polaris system is not simply a large star. It is a star with a rhythm. The rhythm is not visible in the way a lighthouse beam is visible, turning across the sea in bright sweeps. It is slower and more delicate than that. Polaris AA grows a little brighter, then a little dimmer, and then brightens again. The change is small enough that casual stargazing would not notice it. The North Star still seems steady to the eye. It still holds its place near the pole with the same quiet authority. But careful measurement shows that its light is not constant. It pulses. This places Polaris AA inside a rare and useful class of stars called Cepheid variables. A Cepheid is a star that changes brightness in a regular cycle because its outer layers expand and contract. The star is not blinking. It is not being shaded by another object. Its own body is changing. The gas in its outer regions swells outward, cools slightly, and becomes more transparent. Then gravity pulls it inward again. The gas compresses, heats, and traps radiation differently. The surface brightness shifts as the star moves through this repeated motion. It is a kind of stellar breathing, though the star has no lungs and no air. The motion begins deep in the physics of ionized gas. In certain layers of a Cepheid, helium atoms lose electrons and become ionized. When that gas is compressed, it becomes more opaque, meaning light has a harder time passing through it. Radiation builds beneath the layer and pushes outward. The star expands. As it expands, the gas cools and becomes less opaque. Light escapes more easily. The outward push weakens, and gravity begins to draw the layer back down. Compression returns, opacity rises again, and the cycle begins once more. From Earth, this internal engine appears as a gentle change in brightness. The timing of the pulse matters. Some Cepheids brighten and fade over only a few days. Others take weeks. The period is not random. It is connected to the star's true luminosity, the amount of light the star actually produces. A longer period means a brighter Cepheid. A shorter period means a less luminous one. This connection is one of the quiet turning points in astronomy, because it changed variable stars from curiosities into measuring tools. The discovery came from careful work with glass photographic plates. At the beginning of the 20th century, Henrietta Swan Leavitt worked at Harvard College Observatory, studying stars recorded in images of the Magellanic Clouds. These are two small companion galaxies of the Milky Way, visible from the southern hemisphere as faint cloudy patches. They are not clouds in the earthly sense. They are star systems, each containing huge numbers of suns, lying far beyond the main body of the Milky Way. Leavitt examined Cepheid variables in the small Magellanic Cloud. Because those stars were all in the same distant galaxy, they were roughly the same distance from Earth compared with the scale of that galaxy itself. That detail mattered. If one Cepheid looked brighter than another, the difference could not mainly be blamed on distance. The brighter star was likely truly brighter. When Leavitt compared their brightness with their pulsation periods, a pattern appeared. The Cepheids that took longer to complete a cycle were brighter. The relationship was clear enough to become a rule. Measure the period of a Cepheid, and its true brightness could be estimated. Compare that true brightness with how bright it looks from Earth, and the distance could be found. A star became a ruler, not a ruler made of wood or metal, but a ruler made of light and time. Each pulse carried information. Each brightening and dimming marked a distance hidden across space. The method did not require a spacecraft to travel there. It did not require a direct measure across the gulf. It used the star's own rhythm as the key. This is why Cepheids became known as standard candles. The phrase does not mean the stars are identical. It means their true brightness can be known by another property. A candle of known strength looks dimmer as it is moved farther away. A Cepheid works in a similar way, except the candle is a giant star. The room is interstellar or intergalactic space, and the dimming happens across distances too large for ordinary intuition. Before Cepheids, the reach of distance measurement was limited. Nearby stars could be measured by parallax, the tiny apparent shift caused by Earth, viewing them from different sides of its orbit around the Sunday. That method is precise when a star is close enough, but the farther a star lies, the smaller the shift becomes. Past a certain distance, the movement is so small that it presses against the limits of the instrument. Cepheids extended the ladder. Astronomers could use parallax to measure nearby stars. Those nearby measurements could help calibrate Cepheids. Then Cepheids could be used in distant star clusters and nearby galaxies. Later, other distance markers, such as Type Ia supernovae, could be calibrated in turn. The ladder rose outward step by step, each rung depending on the one below it. At the base were nearby stars, shifting slightly against the background sky. Farther up were Cepheids pulsing in other galaxies. Higher still were stellar explosions bright enough to be seen across vast stretches of the universe. Polaris stands near the lower rungs of that ladder. It is the closest known Cepheid to Earth, which should make it especially valuable. A nearby Cepheid ought to be a gift, bright enough to study in detail, close enough for geometric distance measurements, important enough to anchor the calibration of more distant examples. In a simple world, Polaris would be an almost perfect reference point. The world is not simple. The very things that make Polaris famous also make it difficult. It is bright, so bright that some instruments can struggle with its glare. It is not alone, so its companions must be accounted for. It pulsates, so its brightness changes. Its distance has been debated because the measurements do not all settle into the same comfortable number. Each uncertainty spreads outward into the properties that depend on distance: luminosity, radius, mass, and age. A Cepheid is useful because its light follows a pattern. Polaris follows the pattern, but not cleanly. Its pulsations are small compared with many classical Cepheids. The difference between its brighter and dimmer phases has changed over time. For decades, the amplitude of its pulse seemed to shrink, as if the star's breathing were becoming shallower. Then it stopped shrinking. Later, it began to grow again. The period of the pulse has also changed. For much of the recorded history of careful observation, the cycle grew longer year by year. Then, in more recent measurements, the trend appears to have shifted. A star that should help calibrate the universe is itself asking to be calibrated. That does not make Polaris useless. It makes it more important in a different way. A perfect standard teaches one kind of lesson. An imperfect nearby standard teaches another. It reveals where the models are thin. It shows which effects have been neglected. Rotation, mass loss, magnetic fields, companion stars, and the exact stage of stellar evolution may all matter. In a distant Cepheid, some of these complications blur into the measurement. In Polaris, they sit close enough to be examined. The pulse is quiet, but the implications are not small. Every Cepheid exists during a temporary stage of stellar life. A star does not spend most of its existence pulsing this way. It must pass through a region of temperature and luminosity, where its outer layers become unstable in just the right manner. Astronomers call this region the instability strip. On a diagram of stellar brightness and temperature, Cepheids occupy that narrow zone, like travelers crossing a bridge. They enter, pulse for a while, and eventually leave. Polaris may be crossing that bridge in an unusual state. Some models suggest it could be making its first passage through the instability strip, moving rapidly away from its main sequence past. Others suggest a later passage, after deeper changes have already taken place in the star's core. The difference matters because it changes the expected rate of period change, the age estimate, and the interpretation of its mass. The observations do not yet settle the matter with complete ease. The North Star remains slightly out of place. There is a calm irony in that. For navigation, Polaris is valuable because it appears fixed. For astronomy, it is valuable because it does not behave as fixed expectations would prefer. Its visible steadiness hides a physical restlessness. The point near the pole is a living star, expanded beyond its earlier life, pulsing through layers of heated gas, pulled by companions, and carrying a rhythm that connects it to galaxies far beyond the Milky Way. The light that reaches Earth from Polaris is not only a direction, it is a clock. It is a record of swelling and contraction, of opacity and release, of gravity pulling inward and radiation pressing outward. In its small changes, it carries the same principle that allowed astronomers to measure the distance to other galaxies and discover that the universe was larger than the Milky Way. Above the northern horizon, the pulse is hidden by distance and familiarity. The star looks steady. The old guide remains quiet. But inside its light, the universe keeps time. Distance is one of the oldest problems in astronomy. The sky gives direction easily. A star can be above the horizon or below it. It can rise in the east, set in the west, or circle the pole without disappearing. Its color can be seen. Its brightness can be compared with the brightness of nearby stars. But distance hides itself. A small bright star nearby and a large bright star far away can appear nearly the same to the eye. The night does not label depth. It flattens the universe into a dark surface scattered with points of light. For thousands of years, that surface was almost all humanity had. The stars looked fixed not because they were close together, but because they were so far away that their true separations could not be felt. The constellations seemed like patterns on one dome, though their stars lay at very different distances. One star in a familiar shape might be only a few dozen light-years away. Another might be hundreds or thousands. The eye connected them into figures because the mind likes pattern and because depth was invisible. To measure that depth, astronomy needed a ladder. The lowest rung is geometry. As Earth moves around the Sun, nearby stars appear to shift very slightly against the more distant background. This shift is called parallax. It is the same kind of effect seen when a nearby branch seems to move against a far hill as the observer changes position. In space, the change in position is not a step to the side, but the width of Earth's orbit. With observations separated by months, the angle is tiny. For even the nearest stars, the shift is smaller than the eye could ever notice. It must be measured by instruments with patience and precision, but when the angle can be measured, the distance follows from geometry. No assumption about the star's nature is needed. The star can be hot or cool, young or old, bright or faint. If its apparent shift across the sky is known, its distance can be calculated. Parallax is clean, but it does not reach forever. As stars lie farther away, their apparent shift becomes smaller. Eventually, it becomes so small that measurement presses against the limits of the instrument. Better telescopes and space observatories have carried parallax far beyond what earlier astronomers could achieve, but the principle remains the same. Geometry fades with distance. The farther the star, the less it seems to move. Beyond that point, astronomy must borrow light. A star's apparent brightness depends on two things: how much light it truly gives off, and how far away it is. If the true brightness is known, then the distance can be inferred from how dim the star appears. This is simple in idea and difficult in practice, because most stars do not announce their true brightness directly. A faint-looking star may be weak and nearby, or powerful and distant. The two possibilities can look almost identical. Cepheids changed that. Their pulse gives away their power. A Cepheid with a longer period is truly brighter than one with a shorter period. Once the period has been measured, the star's real luminosity can be estimated. Then the light arriving at Earth can be compared with that luminosity. The difference becomes distance, not by stretching a ruler across space, but by listening, in a visual sense, to the slow beat of a star. This is why the phrase standard candle became so important. A candle of known strength can reveal distance by how dim it appears. Cepheids are not candles in any ordinary sense. They are swollen stars, brighter than the sun, passing through an unstable stage of life. But their rhythm makes them usable. Each one carries a built-in clue to its true brightness, and that clue can be read from far away. The power of this method was not only that it measured stars, it measured galaxies. When Cepheids were found in the Andromeda Nebula, their periods and apparent brightness revealed that Andromeda was far outside the Milky Way. It was not a cloud inside the galaxy. It was another galaxy, a huge island of stars in its own right. The scale of the universe widened. The Milky Way stopped being the whole known cosmos and became one galaxy among many. That change did not arrive with a sound. It arrived through small marks of light on photographic plates, through repeated measurements, through stars brightening and fading in a regular pattern. A pulse in a distant galaxy told astronomers that the universe was far larger than the human imagination had comfortably allowed. The ladder grew upward from there. Nearby parallax measurements helped calibrate Cepheids. Cepheids then gave distances to nearby galaxies. In those galaxies, other distance markers could be checked. Among the most important were Type 1a supernovae, brilliant stellar explosions that can be seen across far greater distances than individual Cepheids. These events occur in systems involving white dwarfs, dense stellar remnants that gather matter until they reach a critical condition and ignite in a runaway thermonuclear explosion. Because Type 1a supernovae have similar light patterns, their brightness can also be used as a distance marker. They are not identical in every detail, and modern astronomy corrects for their differences with care, but they are bright enough to be seen across deep cosmic distances where individual Cepheids are too faint to measure. In that way, they form a higher rung on the ladder. Cepheids help calibrate supernovae. Supernovae extend the scale outward to galaxies so distant that their light began traveling when the universe was much younger. Each rung depends on the one below it. That dependence is both powerful and fragile. If the parallax measurements shift, the Cepheid calibration can shift. If the Cepheid calibration changes, the distances to galaxies can change. If those distances change, then the calibration of supernovae can also move. The ladder is not a single measurement. It is a chain of trust, built from different methods that overlap just enough to check one another. Polaris matters because it sits close to the lower part of that chain. As the nearest Cepheid, it should help anchor the relation between period and luminosity. It is close enough for geometric measurements to be attempted with great care. It is bright enough for its light to be studied in fine detail. It is familiar enough that many people can find it in the sky with no instrument at all. Yet that same star refuses to be perfectly simple. Its brightness changes only a little. Its amplitude has not stayed constant over recent decades. Its period has changed in ways that do not fall neatly into one easy story. Its companions add light and gravity to the system. Its distance, though much better constrained than in the past, has not always received the same answer from every method. The more important the star becomes as a calibrator, the more these small complications matter. This is not a failure of astronomy. It is how precision reveals depth. A rough measurement can make a difficult star look simple. A careful measurement shows the hidden structure inside the uncertainty. When instruments become better, they do not always make the universe cleaner. Sometimes they show where the clean model was too thin. They reveal the star spot on the surface, the unseen companion in the glare, the slow change in a pulsation period, the faint disagreement between two distance estimates. A map of the universe is drawn from such details. No one can step outside the Milky Way with a measuring line. No observer can move to the side of a galaxy and look back to compare its true depth. The distances are built from light, motion, rhythm, and explosion. A nearby star shifts against the background. A Cepheid pulses in another galaxy. A white dwarf dies in a brief, brilliant fire. Each phenomenon becomes a mark on the scale. There is something quiet about this kind of knowledge. It does not force the universe to become small. It accepts the distance and finds a way to read it. The gulf remains. The stars remain unreachable in any ordinary sense, but their light carries enough structure to turn darkness into measurement. Polaris is part of that structure. The old North Star once helped sailors and travelers read their place on Earth. Its height above the horizon could tell them how far north they were. Now, in a more delicate way, the same star helps astronomers think about place on a cosmic scale. It links the practical sky of navigation to the deeper sky of distance. It belongs both to ancient travel and to modern cosmology. The light from a Cepheid does not simply arrive. It arrives with a beat. That beat carries luminosity. Luminosity carries distance. Distance carries scale. And scale changes everything. A cloudy patch becomes a galaxy. A galaxy becomes one among billions. A star near the pole becomes a rung in a ladder reaching out through the dark. Above the northern horizon, Polaris remains small. It does not look like a measuring instrument. It does not look like a key to other galaxies. It is only a pale point in the turning sky. But across the quiet work of astronomy, such points become candles, and the candles make the dark readable. A useful star is not always a simple star. Polaris became useful to navigation because it seemed steady. It became useful to astronomy because it was near, bright, and part of a class of stars that could measure distance. On paper, these qualities should make it a clean reference point. A nearby Cepheid, visible in the northern sky, tied to the lower rungs of the cosmic distance ladder. It sounds almost too convenient, as though the universe placed a measuring mark near the pole for the benefit of anyone patient enough to look. The real star is less cooperative. Polaris AA does pulse like a Cepheid, but its pulse has never behaved with the plain regularity that astronomers would prefer from a standard example. The changes in brightness are small. The star does not swell and dim with the broad, obvious rhythm seen in many classical Cepheids. Its variation is shallow enough that, to ordinary sight, it still looks constant. Only instruments reveal the subtle rise and fall. For much of the 20th century, even that subtle pulse seemed to be fading. Astronomers measuring the difference between the brighter and dimmer phases found that the amplitude was decreasing. In simple terms, the star's breathing appeared to become quieter. Earlier observations showed a larger variation in brightness. Later ones showed a smaller one. By the late 20th century, the change had become so slight that some wondered whether Polaris might stop acting like a Cepheid altogether. Then the trend did not continue as expected. Instead of fading into stillness, the pulsation leveled off. Later, it began to strengthen again. The star did not follow the clean line suggested by the earlier data. It changed its mind. In the language of appearance, those stars do not decide anything. Their behavior comes from pressure, gravity, temperature, composition, and time. Something inside Polaris had shifted, or something in the way its layers respond to those forces had changed. The period of the pulse carries another problem. For more than a century, observations showed that the cycle was slowly getting longer. Polaris took roughly 4 days to complete one pulsation, but that period was not fixed. It increased by several seconds each year. In human life, a few seconds sounds like almost nothing. In stellar pulsation, measured across decades, it becomes a strong clue. A changing period means a changing star. Its interior structure is evolving, and the outer layers respond by altering their rhythm. Cepheids are expected to change as they evolve. They cross a region of instability as their temperature and luminosity shift. But the rate of change in Polaris is difficult to place. Some models suggest that such a fast period increase points to a first crossing of the instability strip when a star has recently left the main sequence and is moving quickly toward a red giant state. Other models argue for a later crossing, after the star has already passed through deeper evolutionary changes. The distinction is not a small detail. A first crossing would mean Polaris is moving through a brief and rarely observed stage. The star would be caught during a relatively fast transition, a phase that does not last long by stellar standards. A later crossing would place it in a more common part of Cepheid life, where helium burning in the core changes the star's path across the diagram of temperature and luminosity. Each interpretation changes the expected mass, age, brightness, and future behavior of the star. Then the period began to behave differently again. More recent measurements have suggested that the long increase may have slowed, stopped, or even turned in the opposite direction. The star's rhythm, once treated as a sign of steady evolution, became another unsettled detail. The close companion may play a part. As Polaris AB moves around the primary star, the geometry of the system changes. Gravitational effects, orbital motion, and the way the light is measured can all complicate the pulse recorded from Earth. The inner system is not a silent background. It is part of the measurement. A Cepheid alone would already be a complex object. A Cepheid in a triple system is harder. The primary star is expanding and contracting. A close companion tugs on it. A distant companion shares the system's history. The light from the primary must be separated from nearby sources. The motion of the star must be interpreted through the motion of the system. Every observation carries layers. Distance adds another layer still. Polaris is famous, bright, and near, compared with many stars used in cosmic distance work. Yet its distance has been surprisingly difficult to settle. Parallax should provide the cleanest answer. Observe the star from different points in Earth's orbit, measure its tiny apparent shift, and calculate the distance. But Polaris lies hundreds of light-years away, so the shift is extremely small. The star is also bright enough to create problems for detectors designed to measure much fainter stars. Brightness, which makes it easy for human eyes, can make precision harder for instruments. There is also the matter of the companions. The visible light is dominated by Polaris AA, but the system is not a single point in physical reality. A faint companion lies close, another lies farther out. Their gravity affects motion, and their light must be understood when measuring the primary. A measurement of distance is never only a measurement of distance when the object being measured is a variable star inside a multiple system. Different methods have produced different values over time. Older measurements from the Hipparcos mission placed Polaris at one distance. Later, Gaia measurements have supported another value. Other approaches, using properties of the companions or the pulsation itself, have added their own estimates. The disagreement has narrowed compared with older uncertainty. But the star still carries a history of debate. A small difference in distance changes the inferred luminosity. A changed luminosity changes the inferred radius. A changed radius affects the mass and evolutionary state. The whole picture shifts. This is why Polaris is difficult. Its problems do not remain isolated. A distance uncertainty becomes a luminosity uncertainty. A luminosity uncertainty becomes an evolutionary uncertainty. A period change becomes a clue about internal structure. A companion becomes a correction to motion and light. The star is like a calm surface with several currents moving underneath it, each one affecting the shape of the others. The age problem is one of the strangest currents. If Polaris AA and Polaris B are bound together and formed from the same original cloud, they should share roughly the same age. Stars born together can evolve differently if they have different masses, but their starting time should be common. Yet estimates have suggested a mismatch. The bright Cepheid appears young, on the order of tens of millions of years, while Polaris B appears much older, perhaps closer to billions of years depending on the model used. The two stars seem to belong together gravitationally, but their apparent ages do not sit comfortably side by side. One way to escape this problem is to question the relationship itself. Perhaps the wide companion is not truly bound. Perhaps it is only passing near the same line of sight. But the evidence for a physical connection is strong enough that this answer does not feel fully satisfying. Another possibility is stranger and more graceful. Polaris AA may not have lived its whole life as a single star. It may have been altered by interaction or merger with another star in its past. In dense star clusters, astronomers have long known of blue stragglers, stars that appear younger, hotter, and more massive than the rest of the population around them. They seem to have been rejuvenated by gaining mass, either through collision or through the merging of stars in a binary system. The result is a star that looks younger than its true age, because its fuel, supply, and structure have been changed. Polaris AA may carry a related story. The idea remains speculative. It is not a settled answer, but it shows why the North Star is so hard to place in a clean category. A star's present appearance may not reveal a simple past. Companions may have shaped it. Mass may have been gained or lost. Rotation may have mixed material inside it. Magnetic fields may have altered its surface and pulsation. Stellar winds may have removed outer layers. Each process leaves a trace, but not always a trace that can be read directly. Recent observations have added yet another texture to the problem. The surface of Polaris AA appears to show large star spots, darker or brighter regions linked to magnetic activity. On the Sun, spots are common, shifting marks where strong magnetic fields affect the flow of heat. On a Cepheid supergiant, such spots can influence the measured light and perhaps reveal physics missing from simpler models. The star is not a smooth, glowing sphere. It has weather of a stellar kind. That matters because Cepheids are not merely objects of local curiosity. They help set the scale of the universe. If nearby Cepheids contain physical effects that are not fully understood, then the calibration of distant Cepheids must be handled with care. This does not break the distance ladder. It refines it. It asks for more complete models, better observations, and a willingness to let a famous star remain untidy while the evidence gathers. Polaris is still a guide. It guides by position for the naked eye. It guides by rhythm for distance measurement. It guides by difficulty for stellar physics. Its value no longer comes only from steadiness, but from the way its small irregularities expose the limits of understanding. The North Star does not fail because it refuses to fit. It teaches because it refuses to be reduced too quickly. Above the horizon, it still looks calm. The eye sees a pale point near the center of the turning sky. Instruments find a pulsing supergiant, hidden companions, debated distances, shifting periods, uneven brightness, possible surface magnetism, and an age that may remember an older story than the star's present light admits. The sky gives the simple version first. Astronomy waits for the rest. A map can look finished from a distance. On a printed page, the stars seem to sit in their assigned places. A dot has a name, a line has a coordinate, a constellation has a boundary. Polaris stands near the north celestial pole, and the rest of the northern sky appears to turn around it. The impression is calm and orderly, as if the heavens have been pinned down with enough care to end the matter. But the real map is still moving. Every star has a position, and almost every position is changing. Some motions are fast enough to be noticed across a few years with careful instruments. Others are so slow that they only become clear after generations of observation. A star moves across the sky by proper motion, shifts in apparent position through parallax, approaches or recedes through radial velocity, brightens and fades through its own internal behavior, and sometimes wobbles because another body is pulling on it. None of these motions is large to the eye. Together, they make the sky a living system, rather than a fixed design. Polaris shows this more clearly than its still appearance suggests. The old map placed it near north, because that was enough for navigation. The modern map asks for far more. It wants distance, motion, luminosity, mass, radius, age, surface structure, orbital companions, and the exact rhythm of pulsation. It wants the star not only as a point, but as a physical object inside a system. Every new kind of measurement adds one more layer, and each layer can disturb the simplicity of the one before it. This is where modern astronomy becomes both more exact and less tidy. The Gaia spacecraft was built to measure the galaxy with a precision earlier sky maps could not reach. It scanned the sky again and again, recording positions, motions, brightnesses, colors, and other properties for a vast number of stars and other sources. Its purpose was not to take a single portrait of the Milky Way, but to measure the small changes that reveal depth and motion. A star's location on one day is only the beginning. Its slow drift over time is part of the answer. For many stars, Gaia has sharpened the map beautifully. Distances that were once uncertain have narrowed. Motions that were once hidden have become measurable. Star clusters can be traced through space. Streams of old stars can be followed like faint rivers across the galaxy. The Milky Way begins to show not only where its stars are, but how they are moving. Yet precision does not remove every difficulty. Some stars are too faint, some are crowded too closely together, some are surrounded by dust. Some are not single stars, though they appear that way. Some are variable, changing their brightness while they are being measured. Some are so bright that special care is needed, because the instrument must avoid being overwhelmed by the very light that makes the star famous. Polaris belongs to this difficult side of the map. It is bright. It is variable. It has companions. It sits close enough to be important, but far enough that its parallax remains small. The measurement is not impossible, yet it is not as clean as the star's familiar place in the sky might make it seem. A famous star does not become easy simply because people know its name. Sometimes fame means the eye can find it quickly, while physics still asks hard questions. This is one of the quiet reversals in astronomy. Brightness helps the human observer. It can trouble the instrument. A detector is designed to count light with care. If too much light arrives in one place, the measurement can become difficult, just as a white page under a harsh lamp can lose its fine texture. For a star like Polaris, the problem is not seeing it. The problem is measuring it without being misled by glare, companions, pulsation, and motion. The star is not hiding in darkness. It is hiding inside its own clarity. Hubble helped reveal one of the hidden parts by imaging the close companion. That image did not replace older evidence from spectroscopy. It confirmed a story that motion had already begun to tell. The wobble in the light pointed to a companion before the companion was seen directly. This is how many astronomical maps are built, not from one kind of seeing, but from several kinds laid over each other. A point of light becomes a spectrum becomes motion becomes orbit becomes mass becomes a test of the model. JWST adds another kind of power to this wider practice of measurement. It sees strongly in infrared light, where dust can be less blinding, and where certain stars and galaxies can be studied with different clarity than in visible light. In the distance ladder, its role is not to erase the work of older telescopes, but to check it with sharper eyes in another part of the spectrum. Cepheids in distant galaxies can be measured where crowding, dust, and mixed starlight might have complicated earlier observations. The ladder is not rebuilt from nothing each time. It is corrected. That correction is the life of the map. A parallax value improves. A Cepheid calibration shifts slightly. A supernova distance is refined. A galaxy's place in the cosmic scale becomes a little less uncertain. The changes are small compared with the distances involved, but small changes near the base of the ladder can matter. When the lower rung is adjusted, the higher rungs feel it. Polaris sits close to that base, and so its details have weight. Its distance affects its true luminosity. Its luminosity affects its placement among Cepheids. Its placement affects how models interpret its mass and age. Its companions affect the light and motion used to measure it. Its surface activity may affect the brightness variations recorded from Earth. No single uncertainty needs to be large to matter. In a precise map, even a small uncertainty has a shape. This does not mean the map is weak. It means the map is honest. Older astronomy often worked with large unknowns because instruments could not see the small ones. Modern astronomy sees the small ones and has to live with them. The result can seem less settled, but it is usually closer to the truth. A clean answer may feel comforting. A careful answer often has edges, conditions, and room for revision. Polaris asks for that kind of answer. It is tempting to think of the North Star as a fixed point against which everything else can be measured. Culturally, that is how it has often been used. Scientifically, it is not fixed at all. Its role in the sky comes from Earth's present axis. Its place in space comes from distance measurements. Its motion comes from the galaxy and from its own system. Its light comes from a pulsing star with an evolving interior. Its companions pull on it. Its surface may carry magnetic marks. Its future position in the northern sky will slowly change as Earth's axis precesses. There is no single stillness underneath all of that. And yet, the map can still work. Navigation worked with the apparent steadiness. Astronomy works with the hidden motion. The two are not enemies. They belong to different scales of truth. A sailor did not need the orbital period of Polaris AB to find north. A cosmologist cannot ignore the complications of Cepheids when using them to measure galaxies. The same star can be simple at one scale and difficult at another. That may be the deeper lesson of the modern sky. Better instruments do not make the universe behave more neatly. They make its untidiness visible. Gaia does not freeze the galaxy. It reveals motion. Hubble does not turn a triple system into a single answer. It shows the companion. JWST does not end the distance ladder. It tests where the ladder holds and where dust, crowding, and calibration still matter. Each tool adds precision, and precision brings questions close enough to touch. The old star maps were beautiful because they made the sky readable. The new maps are beautiful in a quieter way. They show that readability is never final. The Milky Way is not a painted ceiling. It is a rotating, breathing, changing body of stars, gas, dust, clusters, remnants, and dark spaces. Its shape is still being measured. Its history is still being reconstructed. Its distances are still being refined. In that moving map, Polaris remains near the pole for now. It still appears steady to the eye. It still waits above the northern horizon, while the constellations circle. But behind the familiar point, the measurements continue. The star's light is compared, corrected, separated, timed, and placed again. A new data release can sharpen the number. A new model can shift the interpretation. A new image can expose one more detail in the glare. The North Star keeps its old place in the night. The map around it keeps changing. A star's life begins in darkness. Before there is a surface, before there is color, before there is anything that would be recognized as a star, there is a cloud. It is cold by stellar standards, wide enough to hold the raw material for many suns, and thin enough that it would feel almost empty if a body could pass through it. Hydrogen drifts there. Helium drifts with it. Dust grains move in the dark, carrying traces of older stars that lived and died before this cloud began to collapse. Gravity works without hurry. A small imbalance forms inside the cloud. One region becomes a little denser than the gas around it. That denser region pulls more material inward, and the extra material makes the pull stronger. The process feeds itself. The cloud folds slowly toward a center. Collapsing gas heats as it falls, not because flame has appeared, but because motion is being squeezed into smaller and smaller space. A dark knot becomes warmer. The warm knot becomes brighter in infrared light. A protostar begins to form. At first, the young object is not yet a true star. It glows because it is contracting. It gathers material from the surrounding cloud through a rotating disk. Jets may stream from its poles, cutting narrow paths into the gas. Around it, the birth cloud remains thick and dusty, hiding much of the light. The star is still being assembled. The decisive change comes when the core becomes hot and dense enough for hydrogen fusion. Hydrogen nuclei begin to join together, forming helium and releasing energy. The star has found the process that will support it for most of its life. Gravity still pulls inward. Fusion pushes outward through heat and radiation. Between those two forces, a balance forms. This balance is called hydrostatic equilibrium. The star does not stop changing completely, but it enters a long, stable phase in which inward weight and outward pressure hold each other in a sustained tension. This is the main sequence. On the Hertzsprung-Russell diagram, Stars in this stage form a broad diagonal band, from hot, bright, massive stars at one end to cool, dim, low-mass stars at the other. The diagram is not a picture of space. It is a picture of stellar condition. It places stars by luminosity and temperature, and from that arrangement, a pattern of life becomes visible. Most stars spend most of their existence on this band, quietly turning hydrogen into helium in their cores. The Sun is there now. It is a middle kind of star, neither among the smallest nor among the largest. Its surface glows with a yellow-white light. Its core converts hydrogen into helium steadily enough that Earth has received a long era of stable warmth. The Sun feels enormous from the perspective of a planet. It contains almost all the mass of the solar system. It holds the planets in their paths. It makes daylight, weather, oceans, forests, and skin possible. Yet among stars, it is not especially large. Move upward along the main sequence, and the stars become hotter, brighter, and heavier. Their light shifts toward blue and blue-white. Their cores are compressed by greater gravity. More pressure means fusion happens faster. More fusion means more energy pouring outward. The star shines with a stronger light, but that strength has a cost. It burns through its fuel at a far higher rate. A heavy star lives like a lamp turned too high. It may contain many times more hydrogen than the Sun, but it spends that fuel with much greater urgency. The relationship is not gentle. A star twice as massive as the Sun does not simply live half as long. It may shine far more than twice as brightly and consume its core fuel far more quickly. The most massive stars can be so luminous that their lives are measured in only millions of years, while smaller stars can survive for billions or even trillions of years. Brightness and longevity move in opposite directions. This is one of the quiet reversals of stellar life. The stars that dominate photographs of young clusters, the blue stars that look most powerful and alive, are often the ones closest to early death. They are visible because they spend energy lavishly. They shape the clouds around them with ultraviolet light. They drive winds into the gas. They carve bubbles in their birthplaces. But they do not last. Their brilliance is a sign not of safety, but of rapid consumption. A red dwarf, by contrast, can burn with great restraint. It is small, cool, and faint. It may not impress the eye across interstellar distance, yet it uses its hydrogen slowly and efficiently. Some red dwarfs may continue shining long after stars like the Sun are gone. The universe is not yet old enough for the smallest of them to have reached the end of their main sequence lives. The heavy stars live differently. Inside a massive star, the core is hotter, denser, and more restless. Hydrogen fusion may proceed through processes that depend strongly on temperature. Energy floods outward. Radiation pressure becomes a major part of the star's internal support. The outer layers are held in a balance that can become fragile as the star grows more massive. Light itself pushes on the gas. Stellar winds become stronger, peeling material from the surface and sending it into space. Such stars are rare. The galaxy makes many more low-mass stars than high-mass ones. A cloud can more easily form small, long-lived stars than enormous blue ones. And once massive stars are born, they vanish quickly by cosmic standards. The result is that they are both powerful and uncommon, like brief blue fires scattered through the spiral arms of the Milky Way. They tend to appear in young regions, where star formation has happened recently enough that they have not yet died. Their effect is larger than their numbers. A massive star can illuminate a whole nebula. Its radiation can ionize surrounding gas, stripping electrons from atoms and making the cloud glow. Its winds can compress nearby material, sometimes encouraging new star formation along the edges of a bubble it has carved. Later, when the star reaches the end of its life, its explosion can scatter heavy elements into space, A single massive star may live briefly, but the material it moves can shape its neighborhood for a long time. The path away from the main sequence begins when hydrogen in the core runs low. For a star like the Sun, this transition is slow and comparatively gentle, though it will still transform the inner solar system beyond recognition. For a heavy star, the change is more violent in structure, though not always outwardly sudden at first. The core contracts, the temperature rises, new fusion stages become possible. Helium can fuse into carbon and oxygen. In the most massive stars, the sequence continues onward through heavier elements, layer after layer, like shells arranged around a deepening center. The star becomes more complicated as it ages. During the main sequence, the core is mostly concerned with hydrogen. Later, the interior can develop layers where different forms of fusion happen at different depths. Hydrogen may burn in a shell outside the core. Helium may burn deeper in. Later stages can create neon, oxygen, silicon, and finally iron in the most massive stars. Each stage lasts for a shorter time than the one before it. The star moves through its final fuels with increasing speed. The outer layers respond to the changing core. As energy flow changes, the star may swell. Its surface cools even as its luminosity remains high, shifting its color toward yellow, orange, or red. A star that was once blue and compact can become a supergiant, enormous in radius but diffuse in its outer atmosphere. Its edge becomes less like a clean boundary and more like a region where gas thins gradually into space. The star has not become calm, it has become vast. This is the larger family to which Polaris belongs in a gentler way. Polaris AA is not among the most massive stars in the galaxy, but it is evolved. It has left the simple stability of the main sequence and entered a phase where its outer layers respond to changes inside. Its Cepheid pulsation is one expression of that transition. In more massive stars, the same broad principle becomes more dramatic. A star leaves its long hydrogen, burning youth, and begins to change shape, color, rhythm, and fate. The Hertzsprung-Russell diagram quietly records these changes. A star does not wander across it like a point on a road map, but its temperature and luminosity shift over time, creating an evolutionary track. A young, massive star begins high and hot. Later, it can move toward the cooler side as it expands. Some stars loop through different regions as core burning stages change. Some cross the instability strip and pulse as Cepheids. Others swell into supergiants and approach the conditions that will end in collapse. The diagram looks still on paper, but it is full of time. A human life sees almost none of this directly. The stars seem fixed because their changes are slow, or because the most dramatic changes are rare. But the galaxy contains stars at many stages at once. One star is being born inside a dark cloud. Another is quietly burning hydrogen. Another is swelling into a giant. Another is losing mass through winds. Another is days, centuries, or millennia from the final failure of its core. Astronomy builds the life story by seeing many stars in different moments and arranging them into a sequence. The heavy stars give the sequence its urgency. They are the makers of short cosmic drama, though the story can be told without haste. Their lives are brief because their light is costly. They do not conserve themselves. They spend their cores quickly, transform their interiors rapidly, and return altered material to space. The universe uses them as furnaces, as sculptors of nebulae, and eventually as sources of the heavier elements that smaller stars cannot easily make. Their beauty is tied to their impermanence. A blue supergiant, shining across a star-forming region, is not a permanent jewel. It is a temporary state of matter under pressure, burning through its available fuel at a speed that guarantees change. The light that makes it visible also marks the pace of its decline. The star is bright because it is spending itself. In the quiet scale of the galaxy, that spending matters. Without massive stars, space would be poorer in heavy elements. There would be fewer shock waves stirring the gas, fewer bright nebulae, fewer supernova remnants, fewer seeds for rocky worlds. The short-lived stars leave long-lived consequences. They do not last, but they alter what comes after them. Polaris, with its measured pulse and difficult properties, opens the door to this wider idea. A star is not a fixed lamp, it is a phase in a long physical process. Some phases are quiet, some are swollen, some pulse, some burn blue and vanish quickly. Each star carries a balance between gravity and pressure, between fuel and light, between what it is now and what its core will force it to become. The northern sky still turns around its pale guide. Beyond that guide, across the Milky Way, heavier stars are living faster lives. They shine with a power that cannot be separated from their brevity. In their cores, hydrogen disappears, helium waits, heavier elements gather. The old balance holds for a while, then changes. Every star is a clock. The massive ones run quickly. The largest stars are not always the heaviest stars. That sounds wrong at first. On Earth, a larger body often suggests more matter, more weight, more substance. A mountain is larger than a stone because it contains far more rock. A planet is larger than a moon because it usually holds more mass. But stars do not follow that simple instinct. A star can become enormous not because it has gathered the most material, but because its outer layers have expanded into a vast, thin envelope. Size and mass part ways in the later life of a star. During the main sequence, the connection between mass, brightness, and temperature is easier to see. Massive stars tend to be hotter and more luminous. Smaller stars tend to be cooler and dimmer. But once the fuel in the core begins to change, the surface can tell a different story from the center. The core may contract while the outer layers swell outward. The star grows larger, even as the amount of matter inside it may not grow at all. A giant is often a star becoming less compact. When hydrogen in the core begins to run low, the old balance changes. Gravity presses inward on the central regions. The core contracts, and that contraction raises the temperature. Around the core, hydrogen may continue to fuse in a shell. Energy from that shell flows outward and pushes on the star's outer layers. Those layers expand into space, spreading the same material across a much larger volume. As the surface moves outward, it cools. The light shifts toward orange or red. The star becomes a red giant. The phrase can make the object sound solid and swollen like a fruit. But the outer regions are not firm. They are gas and plasma held loosely by gravity, extended far from the dense heart of the star. The radius grows. The surface temperature falls. The luminosity can remain high because the glowing area is so large. A cooler surface, spread over an enormous sphere, can still pour out far more light than the sun. The sun will one day follow this path. It is not massive enough to become a supernova. Its end will be quieter than the deaths of heavy stars. But before that end, it will change beyond recognition. As hydrogen in its core becomes exhausted and fusion shifts into shells around the core, the sun will expand into a red giant. Its surface will move outward until the inner solar system is transformed. Mercury and Venus will be swallowed. Earth's fate is less certain in detail, but the planet will no longer be a living world beneath a familiar yellow star. The present sun feels steady because the change is far away. For now, it remains on the main sequence, holding its long balance. But the future red giant is already written into the physics of its core. The light that warms Earth comes from a temporary arrangement. It is stable, but not permanent. Given enough time, even an average star becomes strange. Some red giants are already visible as examples of what that future means. Mira A is one of them. It lies in the constellation Cetus, and it has been known for centuries because its brightness changes strongly over time. It is not a steady red light. It pulses over long cycles, swelling and shrinking, brightening until it can sometimes be seen by the unaided eye, then fading until it disappears from ordinary sight. Its outer layers move in and out like a slow tide of stellar gas. Mira A is not far more massive than the Sunday. That is the important point. It does not need to be enormously heavy to become enormously wide. Its stage of life has changed the way its body is arranged. The core has become compact and hot. The outer atmosphere has expanded. The star's radius can reach hundreds of times that of the Sun, even though its mass is only modest by stellar standards. A small difference in mass can lead to a large difference in appearance when time has done its work. Above a certain mass, the story grows larger again. Stars born with several times the Sun's mass can become red supergiants. These are not simply red giants made a little bigger. They are massive, evolved stars whose outer layers can expand across distances large enough to fill the inner solar system. Their surfaces are cool compared with blue stars, but their total light is immense because their bodies are so wide. Betelgeuse is the nearby example that gives this idea a familiar face. In the constellation Orion, it marks the shoulder with a red-orange light. It is easy to find on a clear winter night. The star is far away, yet it appears bright because it is huge and luminous. If placed at the center of the solar system, its outer layers would extend beyond the orbits of the inner rocky planets. The exact boundary is not a sharp surface, but the scale alone is enough to change the imagination. The Sun would no longer be the central measure. The familiar planetary distances would be buried inside a single star's outer atmosphere. Betelgeuse also change. Its surface is not smooth. Huge convective cells move within it. Far larger than anything on the Sunday hot material rises, cools, sinks, and distorts the appearance of the star. Its outer layers breathe unevenly. Material leaves the star and drifts into surrounding space. Dust can form, brightness can fall and return. To the eye, Betelgeuse is a red point. To instruments, it is a restless supergiant, with an atmosphere too extended and uneven to behave like a simple sphere. This is why measuring giant stars is difficult. A planet has a surface. A rocky world ends where the ground ends. A star does not have a ground. Even the Sun's visible surface is only the layer from which light escapes most easily. For a red supergiant, the problem is larger. The outer gas is thin, moving, and losing material into space. The star may be surrounded by dust and expelled matter. Different wavelengths of light can show different apparent sizes. The edge depends partly on how the observation is made. The largest stars are therefore not only large, they are hard to define. Scuti is one of the names often placed near the edge of this question. It is a red supergiant in the constellation Scutum, far beyond ordinary naked eye visibility. Its estimated radius has made it famous as one of the largest known stars by size. If it were placed where the Sun is, its outer layers would reach far beyond the orbits of the inner planets and toward the realm of the giant planets. The scale is so wide that the solar system begins to feel like a small room inside a larger glow. But Scuti also shows why titles like largest known star must be treated gently. It is distant, it is dusty, it varies in brightness. Its apparent diameter depends on observations that have to pass through interstellar space, through surrounding material, and through models of what counts as the star's edge. Its size has been revised before, and it may be revised again. There are other candidates, other red supergiants and hypergiants, whose radii may rival or exceed it depending on the method used. The title matters less than the lesson. A star can become so extended that its outer atmosphere is more like a region than a wall. The gas is present but thin. The light is strong but spread out. The star is enormous, but not dense in the way a planet is dense. It has grown by opening itself outward, by letting its outer layers occupy space on a scale that ordinary matter rarely does. Its size is partly an act of aging. This is the reversal that makes giant stars so strange. The most massive stars are not always the widest. A compact blue star can hold far more mass than a red supergiant with a larger radius. R13601, one of the most massive and luminous stars known, is far heavier than many red supergiants, yet it is not the largest by radius. It burns with fierce power, sheds mass through intense winds, and lives quickly. A red supergiant may be less massive, cooler, and more diffuse, while still filling a far larger volume of space. Mass tells one story, radius tells another. The human eye tends to imagine stars as bright balls of fire, but stellar bodies are governed by balance, pressure, opacity, fusion, gravity, and time. A star's size is not only about how much matter it contains. It is about where that matter sits, how hot the core has become, how the outer layers respond, and how far gas can be held before it thins into space. In old stars, especially giants, structure matters as much as substance. The outer layers of a red giant are loosely held. Material can be lifted by pulsations, pushed by radiation, and carried away in winds. Over time, a giant star can lose a large part of itself. The loss is not always explosive. Sometimes it is a long exhalation, a steady outward drift of gas and dust. Around aging stars, shells and clouds can form, carrying carbon, oxygen, and other elements into the surrounding darkness. The giant becomes not only a swollen star, but a source of future material. That future material will matter later. It may mix with gas from other stars. It may become part of a dark molecular cloud. It may cool, gather, and eventually help form new stars and planets. A red giant is an ending for one kind of stellar life, but it is also a transfer. Matter that spent millions or billions of years inside a star begins moving outward, leaving the old body and entering the wider galaxy. This gives giant stars a slow dignity. They are not stable in the way main sequence stars are stable. They are transitional. Their shape is changing. Their surfaces are uneven. Their light varies. Their atmospheres leak into space. Yet, they mark one of the great phases of stellar life. The moment when a star that once held itself tightly begins to loosen and expand. For Mira A, the expansion is tied to long pulses. For Betelgeuse, it appears in a vast red atmosphere, convective cells, dust, and changing brightness. For Scuti, it becomes a question of how far a star can spread before the idea of an edge becomes uncertain. Each one shows a different version of the same principle. Stars do not simply shine until they stop. They change form. They swell. They cool at the surface, while their cores become more demanding. They lose material. They move across the diagram of stellar life from the calm band of the main sequence into regions where size, color, and rhythm become less predictable. The giant phase is not a final answer. It is a passage. In the quiet sky, these enormous bodies still look like points. Betelgeuse is a red spark in Orion. Mira can fade until it disappears from sight. Scuti is hidden from unaided eyes entirely. Their true sizes belong to measurement, model, and imagination. Yet their light carries the evidence of stars that have become larger than their earlier selves, not by gaining the universe, but by changing within. A giant star is not merely a big star. It is an old balance coming undone. A giant star does not end where the eye wants it to end. A rocky planet has a surface that can be imagined as a boundary. Stone gives way to air. Ocean gives way to sky. Even a gas giant, though it lacks a solid ground in the ordinary sense, has layers that can be described by pressure and depth. A red supergiant is less willing to be divided so neatly. Its outer body thins gradually. Its atmosphere extends outward. Gas rises, cools, falls, and escapes. Dust forms where the temperature has dropped enough for atoms to gather into grains. The star becomes surrounded by its own loosened material. The edge turns into a question. For a main sequence star like the Sun, the visible surface is already not a solid surface. It is the layer from which most visible light escapes into space. Below it, plasma becomes more opaque. Above it, the gas thins into the atmosphere. The boundary is useful, but it is not a wall. In a red supergiant, that problem grows wider. The atmosphere can be so extended and uneven that the apparent size changes depending on the wavelength of light used to observe it. Seen in one kind of light, the star may appear one size. Seen in another, it may seem larger, because cooler gas and dust farther from the center are glowing or absorbing light. Infrared observations may reveal warm dust. Visible light may be dimmed by that same dust. Radio and submillimeter observations can trace cooler layers that sit above the photosphere. Interferometry, which combines light from separated telescopes to act like a much larger instrument, can resolve structures that ordinary imaging would blur. The star is not only an object, it is an environment. Betelgeuse shows this clearly because it is close enough, as red supergiants go, for its disk and surroundings to be studied in unusual detail. It is not a smooth red globe. Its surface is mottled by enormous convective cells, where hot material rises from below and cooler material sinks again. These cells are not small granules like those seen on the Sun. On a supergiant, a single convective structure can cover a large part of the visible surface. The star's face changes slowly, as if heat were moving beneath a thin red skin. Around that surface lies more uncertainty. Betelgeuse loses material. Gas lifted from its outer layers can drift away, cool, and condense into dust. During its great dimming, the star did not simply fade like a lamp being turned down. Observations point toward a large ejection of material from the star's surface. As that material moved outward, it cooled and formed dust that blocked part of the light from Earth. The star looked weaker, not because it was necessarily close to immediate collapse, but because its own expelled matter had crossed the line of sight. This is the kind of event that makes the edge of a giant difficult to define. The visible star, the extended atmosphere, the cooling gas, and the dust cloud are connected. They are not the same thing, but they belong to one active system. Material that was part of the star becomes material around the star. The boundary is not a clean cut, it is a slow departure. Scuti carries the same lesson on a larger and more uncertain scale. It is often named among the largest known stars, and the scale attached to it is almost too wide to hold in ordinary thought. Placed at the center of the solar system, a star of that kind would stretch across the inner planetary orbits and out toward the realm where the giant planets begin. But such comparisons can make the radius sound firmer than it is. The real measurement depends on distance, brightness, temperature, dust, variability, and the model used to translate light into size. A red supergiant can be famous for its radius, and still have a radius that changes on paper as the measurements improve. This does not make the star less real. It only means the title is delicate. Largest known star is not like tallest mountain, measured from a base to a summit of stone. It is more like asking where a fog bank ends while it is still moving. The star has a body. The body has structure, but its outer layers are diffuse. and the surrounding matter complicates the view. A new distance estimate, a better temperature measurement, or a sharper image of dust can change the inferred radius. Wo 64 makes the problem even richer. It lies far outside the Milky Way, in the large Magellanic Cloud, one of the small companion galaxies that orbit our own. For decades it was known as a very large, dust-enshrouded red supergiant. Its light had to cross not only the space within the Milky Way's neighborhood, but the distance between galaxies. At such a range, even a supergiant is normally only a point. The star's surroundings must be inferred from spectra, brightness changes, and the way dust reshapes the light. Recent interferometric observations have brought that hidden environment closer. The image does not show a clean stellar ball. It shows a compact, elongated glow around the star, a cocoon of gas and dust close to the dying supergiant. That shape may come from uneven ejection, rotation, or the influence of a companion not yet fully confirmed. The important point is quieter than any single explanation. Near the end of a massive star's life, the star can begin to hide itself in the material it has lost. It becomes wrapped in its own past. The dust around a red supergiant is not an ornament. It changes how the star is seen. It absorbs visible light and re-radiates energy in infrared. It can make a star appear dimmer in one band and bright in another. It can disguise the surface and create the impression of a larger or more complex body. It also records mass loss, the slow or sudden movement of stellar material away from the star and into the surrounding space. Mass loss is one of the central uncertainties in the late lives of massive stars. A red supergiant can lose material through winds, pulsations, large convective motions, and episodic outbursts. The rate of loss affects what remains when the core finally collapses. It can influence the kind of supernova produced, the brightness of the explosion, and the remnant left behind. Yet the mechanisms are still difficult to model completely, because the outer layers of these stars are turbulent, extended, cool enough for molecules and dust, and shaped by motions that do not stay perfectly spherical. A simple spherical model often fails. Real giant stars are lumpy. Their atmospheres are uneven. Their dust shells can be clumped, flattened, or stretched. A companion star may pull material into a preferred direction. Rotation may help shape an outflow. Magnetic fields may influence how plasma moves. Pulsations may lift gas to cooler regions where dust can form. Each effect leaves an imprint, but the imprints overlap. The Hayashi limit gives another way to understand why the largest stars cannot grow without restraint. On the Hertzsprung-Russell diagram, very cool, very large stars approach a boundary beyond which stable hydrostatic solutions become difficult. A star pushed too far toward lower surface temperature and larger radius cannot simply remain there in peace. Its outer layers become strongly convective. The structure adjusts. Gravity and energy transport force the star back toward a more stable arrangement. This limit does not give one exact visible edge for every supergiant, but it helps explain why even the largest stars have a physical ceiling. They can swell enormously. They cannot swell forever. This gives the largest known stars a strange status. They are extreme, but not lawless. They sit near the outer possibilities allowed by stellar structure. Scuti, Betelgeuse, WOG, 64, and other red supergiants are not just big objects. They are stars near the edge of what aging stellar matter can do while still holding together. Their size comes from a balance that is already under strain. Inside, the core continues its private work. Outside, the envelope expands, cools, convects, and leaks into space. Between the two lies a star that is hard to draw. Any neat circle placed around it is a convenience. The real object is a layered transition from dense interior to glowing surface, from surface to extended atmosphere, from atmosphere to wind, from wind to dust, from dust to the interstellar medium. The giant does not stop suddenly. It fades outward. This fading outward is part of its legacy. The material leaving the star carries elements made or processed during stellar life. Oxygen, carbon, silicon-bearing dust, and other compounds can move into the surrounding space. Over time, those grains may mix with older clouds and with material from other stars. They may become part of future star-forming regions. Some may eventually be locked into planets, moons, asteroids, or the dark grains inside a cold molecular cloud. A red supergiant is therefore measured not only by radius, but by reach. Its body reaches outward through its atmosphere. Its lost material reaches into space. Its future explosion may send heavier elements even farther. Its influence can continue long after the original star has vanished from the sky. The edge of the star is hard to define because the star is already becoming something larger than itself, a source of matter for the galaxy around it. From Earth, the view remains deceptively simple. Betelgeuse is a red point in Orion. Scuti is invisible without optical help. G64 is far beyond the naked eye, hidden in another galaxy. Their true forms are reconstructed from light gathered patiently, divided by wavelength, compared against models, and corrected for dust. The result is never a perfect portrait. It is a careful approximation of a moving, leaking, glowing, uneven body. That is enough. A giant star does not need a sharp edge to be real. Its uncertainty is part of its nature. The largest stars are not cosmic statues with fixed borders. They are old furnaces wrapped in weather, shedding themselves into darkness. Their surfaces breathing, their atmospheres thinning, their dust drifting away. Their edges are not lines, they are departures. Betelgeuse is one of the few giant stars that feels almost personal. It is not close in any ordinary sense. Its light still crosses hundreds of years before reaching Earth. The star is far beyond the solar system, far beyond the nearest stellar neighbors, and far beyond any distance a spacecraft has traveled. Yet in the winter sky, it appears plainly to the unaided eye. A red-orange point marks the shoulder of Orion, bright enough to belong to one of the most recognizable patterns in the night. That familiarity changes the way its variations feel. Many red supergiants brighten and dim. Many lose material. Many are surrounded by dust. Many pass through late stages of stellar life that are difficult to model with perfect confidence. But most of them are too faint, too distant, or too unfamiliar to enter common memory. Betelgeuse is different. It sits in a constellation known across cultures and seasons. When it changes, the change seems to happen not in a remote catalogue, but in the visible sky. In late 2019 and early 2020, Betelgeuse faded. The decline was large enough to be noticed by astronomers and sky watchers. A star that had long been known as one of the brightest in Orion became visibly weaker. Its red light did not vanish, but it lost much of its usual strength. The effect was soon called the Great Dimming, a simple phrase for an event that unfolded across the surface and atmosphere of a star wider than the inner solar system. For a little while, attention turned toward the most dramatic possibility. Betelgeuse is expected to end as a supernova one day. It is massive enough, evolved enough, and far enough along in its life that its final collapse is part of its future. In astronomical language, it may be close to that end, but close, for a red supergiant, can still mean thousands or tens of thousands of years. The human meaning of soon does not fit easily onto a stellar clock. The dimming did not prove that the final collapse had begun. What the observations began to show was stranger in a quieter way. Betelgeuse had likely released a large amount of material from its surface, Hot gas rose from the star, moved outward through its extended atmosphere, and entered cooler regions above the photosphere. There, some of that material could condense into dust. From Earth, the dust crossed part of the visible disk of the star and blocked a portion of the light. The star looked dimmer because its own atmosphere had placed a shadow in the line of sight. It was not a fading lamp. It was a red supergiant partly hidden behind its own expelled matter. This matters because the outer layers of Betelgeuse are not quiet. The star is enormous, cool at the surface compared with blue stars, and deeply convective. Hot material rises in great cells. Cooler material sinks. The surface is not a smooth sphere glowing with equal brightness in every direction. It is uneven, changing, and marked by motions far larger than the convection seen on the Sunday. One region can become brighter or darker. One plume of hot gas can rise higher. One outflow can carry material into the extended atmosphere. A red supergiant has weather, though not weather in the earthly sense. There is no rain of water, no wind of air, no clouds shaped by oceans and mountains. The weather of Betelgeuse is made of plasma, gas, shock waves, magnetic structure, dust formation, and giant convective motions. The star's surface is not a place where a boundary sits still. It is a region where energy from the interior reaches outward through material that is barely held compared with the deeper layers below. When the great dimming occurred, the southern part of the visible disk appeared especially affected. Images and measurements suggested that one large region had cooled or been obscured, changing the balance of light across the star's face. The visible fading was therefore not simply a uniform reduction in brightness. It had shape. It had direction. The star's disk changed unevenly, like a glowing ember partly veiled by smoke from itself. This image is slow and useful. A red supergiant lifts material. The material moves outward. As it expands, it cools. Molecules and dust grains can form. The dust absorbs visible light and re-radiates energy at longer wavelengths. To instruments studying the star in different parts of the spectrum, the event becomes a layered signal. Visible light fades. Infrared behavior gives another clue. Spectra reveal motion and temperature. Images show asymmetry. No single observation tells the entire story. The star has to be read in pieces. That is one reason Betelgeuse is so valuable. It is close enough and large enough on the sky for its surface to be partly resolved with modern instruments. Most stars are only points. Betelgeuse is still small in the telescope. But it is not only a point. Its apparent disk, atmosphere, and surrounding material can be studied in ways that are impossible for many more distant red supergiants. It becomes a nearby laboratory for the final stages of massive star life. The great dimming did not make Betelgeuse ordinary. It made its complexity visible. Before the event, the star was already known to vary. Red supergiants often pulsate in more than one pattern. Their brightness can rise and fall over hundreds of days and over longer cycles. The outer layers do not respond like a solid surface. They expand, cool, contract, and shift under the influence of interior motions. Betelgeuse had always been changing. The great dimming was simply large enough and strange enough to make the world look again. After the dimming, the star brightened. Its light returned toward more typical levels. The expected supernova did not arrive. Orion kept its red shoulder. The event became less a warning of immediate collapse and more a clue to the processes by which a dying massive star loses material before the end. That clue is important because mass loss shapes everything that follows. The amount of gas a star sheds before core collapse influences the kind of supernova it produces, the material surrounding the explosion, and the remnant left behind. A star's death is partly prepared by what it loses before it dies. In the case of Betelgeuse, the lost material does not leave as a smooth, gentle sphere. It can emerge in uneven outbursts, lifted by convection and waves, pushed through the atmosphere, shaped by turbulence and possibly by magnetic effects. Once outside the hotter layers, the gas cools enough for dust to form. That dust can drift away into interstellar space, carrying matter that once belonged to the outer body of the star. The dust is small, but the meaning is large. Each grain is a record of cooling matter. Each drifting shell becomes part of the environment around the star. Later, if Betelgeuse does explode, the supernova shock will run into material already placed there. The light of the explosion may reveal that surrounding matter, illuminating the history of the star's final centuries or millennia. The space around a dying star is not empty. It is prepared. This is why the Great Dimming is not merely an odd episode in a famous constellation. It is a glimpse of late stellar evolution happening in reach of detailed observation. Betelgeuse is showing how red supergiants can shed themselves before the final collapse. It is showing that a star's apparent brightness can change because of geometry, dust, surface structure, and internal motion, not only because the core has reached its last moment. It is showing that the path to supernova may be marked by smaller departures, some visible, some hidden, some lasting only a season in human time. The final collapse remains ahead. Inside Betelgeuse, the core is moving through the late stages of massive stellar life. Hydrogen burning is long past its simplest central phase. Heavier fuels have taken their turns, or will do so depending on the exact internal state. Eventually, the core will no longer support itself. When iron and related elements dominate the deepest center, fusion can no longer provide the outward energy needed to resist gravity. The core will fall inward. The outer layers will be thrown into space. That event will be a supernova. From Earth, it would be bright, perhaps bright enough to alter the familiar appearance of the night for weeks or months. It would not harm the planet from its distance. It would be a spectacle, but also an ending. Afterward, the red shoulder of Orion would no longer shine as it does now. One of the most familiar winter stars would fade from the constellation, leaving a changed pattern for future eyes. There is no need to hurry that ending. Betelgeuse is already remarkable without exploding. Its present state is rich enough, a red supergiant with a restless surface, an extended atmosphere, convective cells larger than many stars, dust forming from expelled gas, and a future written in the physics of core collapse does not need a sudden finale to matter. The quiet changes are part of the story. The slow loss of material is part of the story. The fact that a famous star can dim for reasons other than immediate death is part of the story. A fading light is not always a final light. Sometimes it is a star passing behind its own dust. In Orion, Betelgeuse still glows. Its color remains warm and red against the colder points around it. The constellation rises, crosses the night, and sinks again. Seasons carry it out of view and bring it back. The star continues its late work in silence, lifting material, cooling at the surface, varying in brightness, and holding within itself the future of a supernova that has not yet come. For now, the red giant waits behind its own weather, and the dust drifts outward. The nearest star is also the easiest one to misunderstand. It rises every morning with such regularity that its presence becomes ordinary. It lights the air, warms the ground, draws water upward from oceans and leaves, and lays shadows across walls and fields. In daylight, it can feel less like a star than a condition of life itself. The sun is simply there, too bright to look at directly, too familiar to seem strange, but familiarity is a kind of veil. From Earth, the sun appears as a smooth disk of light. Its edge seems sharp, its color seems steady, its heat seems constant enough for ordinary life to trust. Yet almost everything that makes the sun physically alive is hidden from simple sight. The star is not a calm lamp. It is a moving body of plasma, layered with magnetic fields, rising gas, falling gas, loops, holes, eruptions, waves and grains of brightness so large that Earth would be small beside them. The visible sun is only one version of the Sunday. To see the rest, astronomy must look beyond visible light. Different wavelengths reveal different temperatures, layers, and motions. Ultraviolet light exposes structures that the human eye cannot detect. Extreme ultraviolet light traces hotter plasma in the outer atmosphere. X-rays show the most energetic regions. Infrared light and radio waves carry other information from cooler or deeper material. The same star changes appearance when its light is separated into these hidden forms. The journey can begin far above the surface, in the corona. The corona is the sun's outer atmosphere, a faint, extended region that is usually drowned by the brightness of the lower visible disk. During a total solar eclipse, when the moon covers the bright face of the sun, the corona appears as a pale halo stretching into space. It looks delicate, almost ghostly, but its temperature is far higher than the visible surface below it, a fact that remains one of the enduring problems of solar physics. The outer atmosphere is hotter than the layer beneath, and the full reason is still being worked out through waves, magnetic fields, and small-scale bursts of energy. In extreme ultraviolet light, the corona becomes structured. Loops appear where magnetic fields guide hot plasma above the surface. Bright active regions gather around complex magnetic knots. Darker regions, called coronal holes, open into space where magnetic field lines do not close back down onto the Sunday. From these open regions, streams of charged particles can escape more easily, forming fast solar wind that travels outward through the solar system. When such streams reach Earth, they can disturb the planet's magnetic field and help feed auroras near the poles. The sun touches Earth in hidden ways, not with solid matter and not with ordinary weather, but with particles and fields moving across the space between worlds. The aurora is one visible answer to that contact. Charged particles guided by Earth's magnetosphere enter the upper atmosphere, where they cause oxygen and nitrogen to glow. A green curtain over a polar night begins, in part, with magnetic openings on a star 93 million miles away. Other structures rise from the sun like bridges of fire. Solar prominences are huge loops or sheets of plasma held by magnetic fields. They can extend far above the visible surface, arching into the corona before falling back or erupting outward. Against the darkness of space at the sun's limb, they appear as red forms in certain wavelengths, curved and suspended. Seen from above in ultraviolet light, similar structures may appear as dark filaments stretched across the disk, because cooler material lies above the brighter surface behind it. The material is not still. Magnetic fields on the sun can twist, shear, and reconnect. When field lines rearrange suddenly, stored magnetic energy can be released in a solar flare. A flare is not an explosion of solid matter. It is a burst of radiation across the electromagnetic spectrum, produced when magnetic stress is converted into heat, motion, and energetic particles. The brightening can happen in minutes. The region around it may glow fiercely in ultraviolet and X-ray light. Sometimes the sun releases more than radiation. A coronal mass ejection can send a vast cloud of plasma and magnetic field outward into interplanetary space. The motion may begin with a structure slowly lifting from the corona, stretching until the magnetic arrangement can no longer hold. Then material escapes, carrying billions of tons of charged gas away from the star. Most such clouds do not strike Earth directly. Some pass harmlessly elsewhere in the solar system. When one does arrive at Earth with the right magnetic orientation, it can disturb satellites, power systems, and radio communication. These events sound forceful, but in the solar image they can look strangely graceful. A loop brightens, a dark filament rises, a wide front moves outward from the limb, The scale is enormous, but the motion can appear slow because the camera watches from far away. Minutes become frames. Hours become a silent unfolding. The sun breathes plasma into space. Some plasma does not escape. Coronal rain forms when hot material in magnetic loops cools, condenses, and falls back toward the surface along magnetic field lines. It is rain only by analogy. There are no water droplets. The falling material is plasma, still hot by earthly standards, guided down curved magnetic paths. In high-resolution solar images, it can appear as glowing beads descending through loops. A return flow in the star's atmosphere. Below the corona lies the chromosphere. This layer is difficult to see in ordinary light because the photosphere below it is so bright. In special wavelengths, however, the chromosphere becomes a restless forest of narrow jets and fine structures. Among them are spicules, thin columns of plasma that shoot upward from the lower atmosphere and vanish within minutes. They rise and fall quickly, covering the solar limb with a hair-like texture when viewed in the right light. Spicules are small only compared with the sunday. Many reach thousands of kilometers above the surface. They may help carry energy and material upward, linking the lower atmosphere with the corona above. Their exact role in coronal heating and solar atmospheric dynamics is still being studied. They show how the sun's layers are not separate shells sitting quietly on top of one another. The photosphere, chromosphere, transition region, and corona exchange motion, waves, heat, and magnetic stress. The visible surface waits below. The photosphere is the layer from which most visible sunlight escapes. It is what the eye imagines as the surface of the sun, though it is not a solid boundary. The sun has no ground. It is plasma throughout, a state of matter in which atoms are ionized and charged particles move freely. The photosphere is simply the depth at which the gas becomes transparent enough for light to stream outward into space. Seen closely, the photosphere is not smooth. It is covered with granules, bright cells of rising hot plasma surrounded by darker lanes where cooler material sinks. Each granule is roughly the size of a large country or more, and yet, on the full solar disk, they merge into a fine, grainy texture. The pattern is convection made visible. Heat rises from below, reaches the surface, spreads, cools, and falls back down. The surface of the sun is constantly being renewed by this churning motion. Among the granules, darker marks appear. Sunspots are regions where strong magnetic fields suppress the normal rise of hot plasma from below. They look dark because they are cooler than the surrounding photosphere, though they are still intensely hot. A sunspot is not a hole. It is a magnetic region, a place where the flow of energy has been altered. Sunspots often appear in groups, and active regions around them can become sources of flares and eruptions. The number of sunspots rises and falls with the solar cycle. Over about 11 years, the sun's magnetic activity moves from quieter phases to more active ones and back again. During active periods, sunspots are more common, flares occur more often, and coronal mass ejections become more frequent. The cycle is not a perfect clock, but it gives the sun a long rhythm beneath the daily steadiness seen from Earth. The star nearest to Earth is therefore full of hidden time. There is the 8-minute journey of sunlight from the sun to Earth. There is the slow rise and fall of magnetic activity across the solar cycle. There are granules lasting minutes, spicules vanishing quickly, prominences holding for days or longer, and plasma loops reshaping as magnetic fields change. There are photons that began deep inside the star long before they escaped from the photosphere. Every layer carries a different kind of duration. This changes the meaning of daylight. The sunlight falling on a window is not a simple beam from a simple disk. It is the final outward stream from a star whose interior is hidden, whose surface boils, whose atmosphere is hotter than expected, whose magnetic fields open into space, and whose invisible wavelengths reveal landscapes no eye could see unaided. The ordinary warmth on skin begins inside a nuclear furnace and passes through layers of plasma before crossing interplanetary space. The sun is not less mysterious because it is near. It is mysterious in a different way. Distant stars hide because they are far. The sun hides because it is too bright, too layered, and too active to be understood by visible light alone. Its nearness gives detail, and detail gives complexity. Every better instrument reveals another motion. A loop, a jet, a dark opening, a falling stream, a magnetic scar, a surface cell rising and fading. The same lesson returns. A familiar object is not always simple. Polaris seems like a single fixed point and becomes a triple pulsing system. Betelgeuse seems like a red star and becomes a dusty, changing supergiant. The sun seems like a steady disk and becomes an ocean of plasma, with weather of light and magnetism. In daylight, the hidden star continues its work. Granules rise and sink, sunspots darken and decay. Magnetic loops arch into the corona. Plasma falls as rain that is not water. Open fields guide wind outward into the solar system. Above the bright surface, invisible light draws structures that ordinary sight would never know were there. The nearest star shines plainly. Its deeper light remains hidden. The stars have always seemed to mark places. From the ground, they mark direction first. A bright star above the horizon can become a sign of season. A familiar constellation can tell the hour of night. Polaris can hold the north for anyone standing beneath the clear sky of the northern hemisphere. Long before astronomy became a science of instruments, mathematics, spectra, and space telescopes, the stars were already a kind of map, but the oldest map was flat. It showed where the stars appeared, not where they truly were. The eye could tell that Sirius was bright, that Betelgeuse was red, that Polaris was steady, that the Pleiades gathered in a small misty cluster. It could not tell how deep the sky was. A near dim star and a far bright star could exchange places in appearance. A constellation could join stars that had never been close to one another in space. The night made patterns out of projection. Astronomy began to give the sky depth. The first reliable depth came from parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant ones. The effect is tiny, but it is geometry. And geometry is a strong foundation. If the shift can be measured, the distance can be found. The star does not need to explain itself. Its color, age, mass, and inner structure can wait. The angle gives the distance. This method built the lowest rung of the cosmic distance ladder. The phrase distance ladder is gentle, but the idea is large. No single method measures every scale of the universe. Nearby stars can be reached by parallax. More distant stars require other clues. Nearby galaxies require brighter markers. Farther galaxies require events bright enough to cross cosmic distance. Each step must overlap with the next, so one method can calibrate another. A ladder rises outward, rung by rung, from the solar system's neighborhood to the deep universe. At the base, the motions are small. A nearby star shifts by a fraction of an arcsecond, a tiny angle on the sky. Space telescopes measure that shift again and again, separating real stellar motion from the motion created by Earth's orbit. Over time, the star's parallax, proper motion, and sometimes radial velocity begin to form a three-dimensional path. A point becomes an object moving through space. Polaris belongs near this lower region, though not without difficulty. It is close enough, compared with distant Cepheids, to be important for calibration. It is bright enough to study, variable enough to be useful, and complicated enough to resist easy interpretation. Its role reminds astronomy that the lowest rung of a ladder must be treated with care. A small correction near the base can matter higher up. A small uncertainty in distance can move luminosity, and luminosity can move the interpretation of a Cepheid's pulse. Beyond the nearest stars, parallax becomes harder. The apparent shift grows smaller with distance until it becomes too fine to measure clearly. Geometry has carried the map as far as it can. After that, astronomy turns towards stars whose light carries a built-in clue. Cepheids are among the most important of these stars. Their value comes from their rhythm. A Cepheid brightens and dims over a period connected to its true luminosity. Measure the period, and the star's real brightness can be estimated. Compare that real brightness with the light received at Earth, and distance appears. A pulse becomes a measure. This is a strange and quiet idea. The distance to a star or galaxy can be found not by crossing the space between, but by waiting for a star to breathe in light. The timing of the pulse carries information about the star's power. The dimming of that power across space carries information about distance. The two pieces meet in the measurement. Cepheids opened the nearby universe. They allowed astronomers to measure distances beyond the Milky Way. In distant galaxies, individual Cepheids could be identified and followed through their cycles. Their periods gave their luminosities. Their apparent brightness gave their distances. A cloudy patch in the sky became another galaxy, not a small object within the Milky Way. The universe widened because certain stars changed brightness in a readable way. The light did not need to be loud. It only needed to be regular. Farther out, even Cepheids become too faint to serve alone. Their individual pulses disappear into distance, crowding, dust, and the limits of resolution. The ladder needs another rung, one that can be seen across much greater spans. Type 1. A supernovae serve that role. They are brief, brilliant stellar explosions associated with white dwarfs in certain systems, and their light curves can be used to estimate their true brightness after careful correction. A supernova is not steady like a Cepheid. It is a single event, rising and fading, but its pattern matters. The way the light brightens, peaks, and declines carries information. Because these explosions can become bright enough to rival the light of an entire galaxy, they can be observed at distances where ordinary stars cannot be separated. Cepheids calibrate type 1. A. Supernovae in galaxies close enough for both to be measured. Then supernovae carry the distance ladder outward into regions where the expansion of the universe itself becomes part of the story. At those distances, light is no longer only dimmed by space. It is stretched by the expansion of the universe. Wavelengths lengthen as space itself expands during the journey. This stretching is called redshift, because visible light shifted in this way moves toward the red end of the spectrum. The greater the redshift, in a broad cosmological sense, the more the universe has expanded while the light was traveling. Distance, time, and expansion begin to join one another. The ladder, then, is not just a tool for measuring where things are. It is a tool for measuring what the universe has done. The distances to galaxies help reveal how fast space is expanding. Supernovae helped show that the expansion is accelerating. Cepheids help calibrate the supernovae. Parallax helps calibrate the Cepheids. Nearby geometry reaches upward into cosmology. A tiny shift in a nearby star and a fading explosion in a distant galaxy become parts of one long chain. This chain is powerful because it is layered. It is also delicate because every layer has its own uncertainties. Dust can make a star look dimmer than distance alone would allow. Crowded fields can blend starlight together. Metallicity, the abundance of elements heavier than helium, can affect stellar behavior and brightness. Cepheids may not all be perfectly simple. Supernovae require corrections. Parallax measurements require careful treatment of motion, brightness, and instrument limits. None of this makes the ladder useless. It makes it real. A real ladder is inspected. Each rung is checked against another. Cepheid distances are compared with other methods. Supernova calibrations are refined. Gaia improves nearby distances. Hubble and JWST examine Cepheids in other galaxies with sharper vision and different wavelengths. Infrared light can help reduce the effects of dust. Better data does not end the work. It narrows the questions and reveals which small details still matter. Polaris returns quietly to this larger picture. It is no longer only the North Star. It is part of a family of stars that taught astronomy how to measure beyond the reach of parallax. It is also a warning against treating any calibrator as too simple. Its companions, shifting pulse, debated properties, and evolving surface, all show that even a nearby standard candle must be understood as a physical star, not only as a number in a formula. The same is true across the sky. Betelgeuse is not only a red point in Orion, it is a changing supergiant wrapped in material it has lost. Scuti is not only a candidate for enormous radius, it is a distant, diffuse, variable star with an edge that depends on how it is observed. The sun is not only the daylight source, it is a layered plasma body whose hidden light reveals loops, spots, holes, rain, and wind. Every familiar star becomes more complicated when the measurement deepens, and yet, through that complication, the universe becomes more readable. The map is not made by pretending stars are simple. It is made by learning which complications matter. A companion star changes motion. Dust changes brightness. A pulse reveals luminosity. A spectrum reveals velocity and composition. A surface spot changes a light curve. A supernova decline rate gives a distance. Each piece of light is imperfect alone, but together the pieces form a scale. The old navigator looked north and found direction. The modern astronomer looks into starlight and finds distance. Both acts depend on trust, but not blind trust. The sky must be watched repeatedly. The star must be measured more than once. The pattern must hold. The correction must be understood. Slowly, through repetition, a point of light becomes a coordinate in 3 dimensions. Then it becomes a rung. Then the rung helps lift the map outward. There is a quiet continuity in that. Polaris guided movement across Earth. Cepheids guided thought beyond the Milky Way. Supernovae guided measurement into the expanding universe. The stars are not only objects shining in the dark. They are markers, clocks, furnaces, histories, and instruments written in light. They locate human beings first on a planet, then in a galaxy, then in a universe whose scale still resists any complete image. The night sky remains visually simple. A few bright points, a dark background, a familiar constellation, a red star low in winter, a pale North Star near the center of the turning. But behind that simplicity is a structure of distances, motions, ages, and transformations. The stars are not fixed jewels on a ceiling. They are moving bodies whose light has crossed years, centuries, thousands of years, or millions of years before arriving. Some light gives direction, some gives rhythm, some gives distance. Together, the stars make the dark readable, not by removing its vastness, but by placing small, patient marks within it. A map of the universe is never finished. It is revised with each better measurement, each cleaner image, each pulse timed again, each supernova followed into fading. The map moves because the universe moves, and because understanding moves with it. Above the northern horizon, Polaris still appears calm. Far beyond it, Cepheids pulse in distant galaxies. Farther still, Supernovae rise and fade like brief signals across expanding space. Between them all, the ladder holds, not as a perfect structure, but as a careful one, built from light that left stars long before it reached the instruments waiting here. The stars keep shining. The measurements keep listening. What they listen for is not sound. Space does not carry sound in the ordinary way, because there is no air between the stars to vibrate against an ear. But light carries its own form of speech. It carries color, timing, brightness, motion, and the faint fingerprints of atoms. A star does not speak, yet its light arrives with a pattern. The pattern can be separated, measured, compared, and placed beside other patterns from other stars. Slowly, a distance appears where there had only been darkness. This is why the universe is not completely silent to astronomy. A spectrum can reveal what a star is made of. Thin dark lines, crossing a band of color show which atoms absorbed certain wavelengths before the light escaped. Hydrogen leaves one pattern, calcium leaves another, iron leaves another. The lines can shift if the star is moving toward or away from Earth. They can broaden if the star is rotating quickly or if pressure and heat have changed the way atoms behave. A beam of starlight, spread out carefully, becomes a record of motion and matter. Brightness gives another kind of record. A star's light may be steady across many nights, or it may rise and fall. Some changes come from pulsation, as in Cepheids. Some come from one star passing in front of another, in an eclipsing binary system. Some come from spots rotating across the visible face of a star. Some come from explosions, eruptions, dust clouds, or the slow cooling of a stellar remnant. Every change has to be treated with caution. The same dimming can have more than one cause. The same brightening can hide more than one process. The sky asks for patience. One observation is a glimpse. Two observations begin a comparison. Many observations, repeated over nights, months, years, and decades, begin to show a pattern that can be trusted. The pulse of a Cepheid is not known from a single look. The path of a companion star is not understood from one image. The proper motion of a distant star is not revealed by one point on a chart. Astronomy often works by returning to the same light again and again, letting time become part of the instrument. Time gives the sky depth in a second way. The farther light travels, the older it is when it arrives. Nearby starlight may have crossed only a few years. Polaris sends light that has travelled for centuries. Cepheids in nearby galaxies send light from far deeper in the past. Supernovae in distant galaxies may appear as they were when Earth itself was in a different chapter of its history. Looking outward is also looking backward, not because the past is being imagined, but because light requires time to cross space. The distance ladder is therefore also a ladder of memory. At its lower rungs, the stars belong to a relatively recent past. Their light left after many human civilizations had already risen. Farther out, light left before recorded history. Farther still, before modern humans existed. In the deep universe, the light used to measure expansion may have begun its journey before the Sun had completed many of its own orbits around the Milky Way. Every distance measurement carries a date hidden inside it. This makes the act of measuring strangely delicate. A galaxy is not being seen as it is now. It is being seen as it was when its light departed. A supernova is not exploding now in the distant galaxy. At least, not in the simple human meaning of now. It exploded long ago, and only now does its light reach the instruments waiting near Earth. The cosmic map is built from signals of different ages. It is not one single present moment spread across space. It is a layered view of time. Yet the map still works. It works because physics leaves patterns that can be followed across those layers. A Cepheid pulse has a relation to luminosity. A type 1. A supernova has a light curve that can be corrected and compared. Redshift reveals the stretching of light during cosmic expansion. Parallax fixes the nearby scale. The methods are different, but they overlap enough to support one another. No single star carries the whole universe. No single explosion carries the whole scale. The strength comes from the chain. The chain is never finished. A new telescope can reduce the blur around distant stars. A new detector can measure a faint change more cleanly. A new model can include dust more carefully, or adjust for the chemical content of a star, or separate one star's light from another in a crowded field. Sometimes the improved measurement confirms what was already believed. Sometimes it shifts a number slightly. Sometimes the shift is small enough for ordinary speech to ignore, but important enough for cosmology to notice. This is why precision can feel unsettling. A rough universe is easy to describe. A precise universe has questions at the edges. It asks whether a Cepheid in one galaxy behaves exactly like a Cepheid in another. It asks whether dust has been fully corrected. It asks whether supernovae are as uniform as they first appear after calibration. It asks whether nearby measurements and early universe measurements are pointing to the same expansion rate, or whether some deeper physics is still missing from the model. The question does not need to be dramatic. It can remain quiet and still matter. The stars do not answer all at once. They answer by being measured again. Polaris is measured again. Cepheids in other galaxies are measured again. Supernovae are watched from their first rise through their long fading. Galaxies are surveyed. Star clusters are mapped. The sun is observed across wavelengths no eye could see unaided. Betelgeuse is watched through seasons of brightness and dust. Each object keeps its own rhythm, and astronomy builds meaning by placing those rhythms beside one another. A person standing under the night sky sees only the simplest layer. The North Star is north. Orion is winter. The Milky Way is a pale band when the air is dark enough. The stars seem calm because their distances hide their motion and their changes are too slow or too subtle for unaided sight. This simple sky is not false. It is only the first page. Behind it lies the measured sky, where every point is a moving body. Every color has a temperature. Every pulse has a period, and every brightness has to be corrected for distance, dust, and time. The first page is still beautiful. It does not need the equations to be worth looking at. A dark field, a cold horizon, and a pale star near the northern pole are enough. But the deeper page gives that beauty another dimension. It shows that the same star used for direction can also belong to a problem in stellar evolution. The same red point in Orion can reveal the unstable outer life of a supergiant. The same sunlight on a morning wall can be traced back through plasma, magnetic fields, and nuclear fusion. Nothing familiar stays flat for long. The universe gains depth whenever light is read carefully. A point becomes a star becomes a system becomes a clue becomes a rung on the ladder. The ladder reaches outward, not to conquer the distance, but to acknowledge it with care. The darkness remains wide. The stars remain far. The map remains unfinished. And still, the work continues. The old night sky turns above Earth with the same slow patience. Polaris holds near the center for this age. Cepheids pulse where no eye can see them directly. Supernova light crosses expanding space. Dust dims what must be corrected. Spectra carry the marks of atoms. Parallax shifts by angles almost too small to imagine. The instruments wait, gather, compare, and return. The stars keep shining. The measurements keep listening. The journey can quiet down now. The northern sky remains where it has always seemed to be, turning slowly around its pale center. Polaris still waits near the pole, no longer only a point of direction, but a star with companions, rhythm, uncertainty, and light that has crossed centuries to arrive. Around it, the wider story of stars grows softer. Cepheids pulse in distant galaxies. Red giants loosen their outer layers. Betelgeuse glows behind its dust. The sun continues its hidden motion, lifting plasma into loops, sending wind through space, and shining through the ordinary daylight of a small world. All of it can rechada. The measurements can rest. The distances can fade back into the dark. The diagrams, names, pulses, and stellar winds can drift away like faint sparks carried outward from a dying ember. Nothing needs to be held tightly now. The stars do not hurry. The galaxy does not hurry. Light travels in silence across years, across dust, across the wide spaces between one sun and another. There is only the dark, and the small marks of light within it. A star that once guided travelers still holds its quiet place. A red giant breathes through its outer atmosphere. A hidden companion moves slowly in an orbit almost too long to imagine. Farther away, galaxies turn, supernovae fade, and the great ladder of distance rests on pulses too gentle for the eye to see. The universe remains vast without needing to be solved. For now, it is enough to let the sky be wide. Enough to let the stars keep their patient light. Enough to feel the night settle into stillness, while Earth turns gently beneath it, carrying every sleeping room, every quiet breath, and every closed eye under the same dark, turning sky.